Welcome again to Symbolic Logic. I'm Mark Story. This is Bellevue College. For this short video, we're going to take a look at using truth tables to determine if arguments are valid or invalid. The excitement never stops. Let's take a look at these two arguments. These are simple arguments, granted. There's two different letters in each, which means we have 4 lines. We have B's and A's. In this other argument, we have R's and D's. In video 2, we saw how to set up these truth tables. So this one's set up. I have true, true, false, false under the first letter, and under the next different letter, 1 true, 1 false. We know how to do that now. So what we're going to do is have an argument written horizontally, just by convention. And the slash and double slash isn't a new symbol we have to learn. It's just going to be my way of separating the premises. So I'm going to separate the premises with a single slash, and off to the far right, we'll have the conclusion. And I'll just use a double slash to indicate that. So we have, in this case, 2 premises and a conclusion. Same down here, 2 premises and a conclusion. You can have 1 premise. Some arguments have 3 premises, 4, 5, it doesn't matter. So the idea is we do a truth table underneath the entire thing, and then we just fill in blanks exactly as we did before. Nothing changes. So let me go ahead and fill these blanks in, say for this first argument. And notice this argument here. This would be something like, Yogi's a bear, and if Yogi's a bear, then he's an animal. Therefore, Yogi must be an animal. Well, those premises would guarantee the conclusion, so it's clearly a valid argument. Down here we have an example of an invalid argument. The U.S. president is a Republican or a Democrat, but he's not a Republican. Therefore, he's not a Democrat. Well, the conclusion should have been he would be a Democrat. So what we've got here is a bad conclusion, a bad argument. I want it to look clearly invalid, so we see what happens differently with the truth tables. So we'll fill the blanks in a perfectly normal way. I'll be consistent, make all the A's true, true, false, false. And I'll make all the B's true, true, false, false. Just like we did before. And we can fill in the rest of the blanks. The only blank I have left here is the horseshoe. The only way a horseshoe is false is if the antecedent is true and the consequence false. In every other case, it'll be true. And I'll go ahead and star the main operator for each column. So it's a complete truth table now. We've done nothing different than before. But if we understand the notion of validity, this will now make complete sense. An argument will be valid if it's impossible for the premises to be true and the conclusion false. Well, there's only 4 possible combinations here. So what I'm looking for is a row where the premises, in this case there's 2 of them, are both true and the conclusion's false. This first row, the premises are both true, but the conclusion's not false. That's not going to do it. I want true premises, false conclusion. True premise, but that premise isn't true. In this case, row 3, the first premise isn't true, and same here. It looks like there is no row where we have true premises and a false conclusion. I'm going to call that the tough row, or the tough row. All the premises true and the conclusion false. Tough is bad, hard is bad, bad is invalid, bad. I don't see a tough row, therefore the argument is valid. Happy day. Okay, let's take a look at an invalid argument. With an invalid argument, by definition, it's possible to have true premises and a false conclusion. So I should find a tough row, if you will, a row where all the premises are true and the conclusion is false. So I'm going to quickly fill in these blanks. I'm going to do it exactly the way we've been doing it. I'll be consistent and make the columns underneath each letter the same. So if R is true, true, false, false, I'll do the same for each R's. If D is true, false, I'll do the same for all the D's. And now I'll fill in the tildes. All a tilde does is make the column next to it the opposite. And finally, I'll fill in this wedge. And we know how to do that already. The only way a wedge is false is if both sides are false, like that one here. All these others are true. Okay, let's take a look at this. We've got the truth table completely filled out. No changes, nothing different from before. What I'm looking for is the special tough row, a row where all the premises are true and the conclusion is false. Doesn't happen on the first row because here's a false premise. But check out this. On row 3, all the premises are true and the conclusion is false. That tells me it's possible with this argument for the premises to be true and the conclusion false. And by definition, that makes it an invalid argument. So do a complete truth table, fill in all the blanks, and then look for a tough row. If you find a tough row, it's bad, invalid. If you don't find a tough row, it's not there, then it's a valid argument. It's a good argument.